Alright, so let's see the audio. At least now we know the cause of the issues. So let me share the video that we were watching. So this is the video. Let me go to Discord and remove the audio issues. So on Discord, no more cancellation, no interference. Okay. And okay, we're at 100% on Discord. Audio settings on StreamYard is good. Let me watch. No, I'll just turn on my iPhone. Let's go watch today's stream on my iPhone. So what? That's not it. Let's refresh. So where's my live video? This is it, okay. Okay, it's too quiet. Why is it so quiet? 100%. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, it's louder now. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let me see. Yeah, it's 100%. 1, 2, 3, 4, 5. It's not loud. Oh, if I go to 100%, it's better. Okay, it's good enough. Let me put this here and this here. Okay, so so let's get back. Oh my god. Alright, so let's get back to the video we were watching yesterday. I think this is it.
Frequencies of the EM condition at X. That is, therefore, the always support is parallel to the wall. However, a metallic, then we find this purple expression moves away from equilibrium rather than the spectral radius of metal. As black body, as a function of the walls of the cube are uniformly heated to affect emitter of radiation. Furthermore, experiment shows that the wavelength intensity profile of a black body has a universal character, which does not depend on the shape or composition of.
So I think this is still the introduction. This is not the actual video
of the black body, but only on its temperature. It is this relative simplicity that makes the black body highly appealing to physicists and the logical starting point for any inquiry into the radiation properties of hot objects. An example of a real black body studied by physicists is called the Jeans cube, named after the
So I think this is the actual video, okay.
Physicist Sir James Jeans, who, along with Lord Rayleigh...
Okay, Rayleigh is a famous name, because ultimately it's his empirical, or he got the equation. Anyway, his name I've heard before about the ultraviolet catastrophe.
Provided one of the first attempts to explain the radiation emitted from a black body. A Jeans cube can be thought of as a cubic metallic box with a very small hole in one of the sides.
So it's a cubic metallic box with a small hole at its side, okay.
Radiation incident upon the hole from the outside will enter the cube and reflect back and forth off the walls until it is absorbed. Given that the hole is very small, only a tiny fraction of the radiation...
This is what I don't understand. Some people, when they show this experiment, they're showing a heated body inside. Now, hold on. Did they say they heat up this box?
With a very small hole. Rayleigh provided one of the first attempts to explain the radiation emitted from a black body. A Jeans cube can be thought of as a cubic metallic box with a very small hole in one of the sides. Radiation incident upon the hole from the outside will enter
So it does, they don't heat it up. So I'm confused as to the experiment protocol.
the cube and reflect back and forth off the walls until it is absorbed. Given that the hole is very small, only a tiny fraction of the radiation inside the cube will ever escape back through the hole. Therefore, from the hole's perspective,
Why would you assume that more radiation goes in than goes out? So I guess because internally it's black. Did they say that internally it's black? Did they paint it black on the inside?
from a black body. A Jeans cube can be thought of as a cubic metallic box with a very small hole in one of the sides. Radiation incident upon the hole from the outside will enter the cube and reflect back and forth off the walls until it is absorbed. Given that the hole is very small,
So it's not heated and it's not painted black.
only a tiny fraction of the radiation inside the cube will ever escape back through the hole. Therefore, from the hole's perspective, essentially all
What do you mean from the hole's perspective?
radiation incident upon it will be absorbed, and therefore the hole acts like a black body. We can also
I don't know what it means to act like a black body. I guess like a black body absorbs, if it's painted black, it absorbs more than it emits.
consider the reverse process, in which the walls of the cube are uniformly heated to some temperature,
Okay, so there's two protocols. So one protocol is a cold, unpainted box, okay?
absorbed, and therefore the hole acts like a black body. We can also consider the reverse process,
So there is a reverse protocol.
in which the walls of the cube are uniformly heated to some temperature, such that the walls start emitting radiation and filling the cube. Given that a small fraction of this radiation will then escape through the hole, we see that the hole acts like an emitter of radiation. Since we have already established from the absorption properties of the hole that it behaves as if it is a black body, it follows that the radiation emitted from
Very confusing.
the hole that it radiation. Since we have already established from the absorption properties of the hole that it behaves as if it is a black body, it follows that the radiation emitted from the hole should have the intensity profile of a black body.
I don't know what the intensity profile even means. This is really confusing. I mean, he's talking so much, just showing a box with a black dot and two guys next to it. I am so confused.
Furthermore, since the hole is simply sampling the thermal radiation
I mean, you could show the actual experiment. I mean, this is such a foundational experiment. You'd expect people to reproduce it, to explain it. You expect to find these things on YouTube. Okay, maybe we should look for this experiment on YouTube, because this is no good. I mean, he's showing one picture and talking for 10 minutes straight about the picture. There's a bunch of protocols that we can follow. Words, words, words. Fantastic.
inside the cube, it is clear that the radiation inside the cube should also have the wavelength intensity profile of a black body. Groundbreaking experimental work into the radiation properties of idealized black bodies was carried out by Otto Lummer and Ernst Pringsheim, and these experiments provided valuable data for theoretical physicists to investigate. The experimental work involved
That's great. So there's no y-axis. The x-axis is mu, which I assume is frequency. That doesn't make any sense. It's wavelength. That should be lambda. What is mu? Well, these graphs I'm assuming are different temperatures. This is all they have. So we're supposed to study a seminal experiment from hand drawings from 1,000 years ago. What the heck is going on? And I don't know, does it say stuff in German on this thing? Well, at least it says here 1377 degrees absolute. I'm assuming Celsius or Kelvin, I don't know. 1087, 836. I don't know what the y-axis is. I don't know if they had a y-axis. 1, 2, 3, 4, 5, 6. 6 what? What What are we looking at? How did they plot these? Can we please get the protocol of how to run this experiment?
Measuring the spectral radiance of the black body as a
What the heck is it? How did you plot these points? Could you please tell me how you plotted these points? Please, I'm not asking for that much. And what is this? And what is this? What is going on here? What does it say here? Bubashtet? Beredinet? Birdmet? I don't know what's going on here. This is putting me to sleep.
function of wavelength. This resulted in...
So this is lambda. So lambda is 1, I guess. Oh, this is micrometer. Okay, so lambda in micrometers. So this is gamma 6. I mean, there's no way. I mean, if this is micrometer, I think micrometer, like 0.65 is the color red. And 0.65 is the biggest wavelength. Smaller than I don't get it. Is it 0.6 or is it 6? So this is visual red. So these are bigger wavelength. That's slower frequency. So it's less energetic. This is high energy. But the numbers don't make any sense.
Characteristic curves which varied with temperature. The lower the temperature, the flatter the curve.
Okay, the lower the temperature, the flatter the curve. What does that mean? So the dispersion of the colors. So what he's saying is, right, at this temperature, there is these colors. You look through a spectrum analyzer. At this temperature, you look through this spectral analyzer, and you know, it's long wavelengths. Let's say it's redder. Now, as it gets hotter, there's more stuff in the shorter wavelengths. As it gets hotter, there is even more spectral radiance in the shorter wavelengths. But there's nothing at 0 wavelength. There is no 0 wave. There's no such thing. So wavelength, it's like it's limited. There's very few very short wavelengths. Okay.
The spectral radiance is defined as the energy per...
Let me check the audio. Oh, the audio is dropping. Why is the audio still dropping? Let me check. Discord. What is going on with Discord audio? So everything is off. No, everything is off. It shouldn't be. Don't do preview. I'm so tired. Oh my god. So I don't know what's going on. 1, 2, 3, 4, 5, 1, 2. Alright. What could be is maybe I need to leave Discord and come back. And maybe now it will stabilize without modifying the audio. 1, 2, 3, 4, 5, 1, 2. No, it's still dropping. Okay, so we just need to leave Discord. I don't want to leave Discord. 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 1, 1, 1, 1, 1, 1, 1, 1. Yeah, still dropping, still dropping. But who's causing the drop? What else could it be? I don't know. Completely drop and refresh. Let me see. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, now nothing is happening. 1, 2, 3, 4, 1, 2. Nothing is happening. Oh, even though the mic is quiet. Join. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Now it seems to be stable. Okay. So that's what I need to do. Okay. Maybe, no, I cannot drink more coffee. I should have, but now it's too late. Okay, so, I'm not following. I mean, I'm beginning to understand this experiment. I'm beginning to understand the plot. So this plot, can I reproduce this? So I need to take a black box. I don't have a spectral analyzer. So how would you build a spectral analyzer? So we need to look into how to build a spectral analyzer. But using a spectral analyzer, you could look into the hole of the black box. Now you can heat up the black box. So it's a steel box with a hole, and then you heat it up to 836, and you see that it's right. It's, I don't want to say average. It's difficult to say average, but you know, it's the center of. Let's talk about the center of mass of this area. The center of mass, you could say, is about here. So it's longer wavelengths compared to the center of mass, let's say, of this one, which is again longer wavelengths than the center of mass of this guy, which is a little bit a little bit smaller wavelength. So the wavelengths, the average wavelength goes smaller and smaller as you heat it up, meaning it becomes brighter and brighter, more whiter, bluer, whiter colors. This is blue and this is red. This is more towards the red, more towards the blue. Alright, but the question is, why is it always 0 at lambda, with lambda equals 0? What does it look like internally? So internally, you have to assume that thermodynamically, you're shaking atoms. You're causing the atoms to jiggle using heat, the atoms. A jiggling atom has an electron, so you're shaking up the electron. As you're shaking, did I fall asleep? I think I fell asleep. As you shake the electron, as you jiggle the electron, it goes up and down and emits light, emits radiation, electromagnetic radiation, and emits light. It goes up and down emitting light. Oh my god. Oh my god. What am I supposed to do against this unbelievable, how do you say, like, I'm tired? I don't even know the word. Anyway, what's the models? So they didn't have a model, but why is it a problem? I mean, the more you jiggle, right? The more you jiggle, the faster you jiggle. But there's like, you can't jiggle the atom faster and faster, right? The atom has an eigenvalue. It has a self-resonance. So you have a bunch of atoms in this box, and you can jiggle them more and more, but really you're jiggling them in their own eigenvalue. You cannot jiggle them beyond their eigenvalue, beyond their self-resonance. It's not going to help you. It's just going to hurt you. I keep falling asleep. I don't know what to do. Oh my god. Terrible. Just terrible. Yeah, I slept very poorly last night. Very, very poorly last night. Oh my god. I can go eat something to stay up, or I can go take a nap. Anyway, yeah, maybe we'll go take a nap. I don't have a choice. Okay, there's 4 people watching. We do it for Johnny, man. We do it for Johnny. Okay, let's keep going. Let's keep going. Anyway, so what's going on? So let's listen to what they say. So they say that R, the spectral radiance, the radiance as a function of lambda, energy per second. Okay. So I would say this is the result of a spectral analyzer, right? The spectral analyzer tells you what colors compose a certain radiation, and it tells you how much of each. And this is like a Fourier analysis. It's a Fourier frequency analysis of a wave, because really what you have is a mixed wave, right? The light at this temperature, at 1377, the box is radiating with a certain color, but that color, it's really just a composition of waves. Now each wave is just a frequency. That's all it is. It's a frequency and an intensity. So for each frequency, there is an intensity. So for very high frequency, this is very high frequency because it's very short wavelength. So it's a very high frequency. So there is very little radiation, very little events of this type. Now as you keep going to higher frequency, which is the color. So this is the color. The wavelength is the color. So this is lower. As you move to the right, it's lower frequency, lower energy. So on the left is the maximum energy, like you could say gamma. Gamma or ultraviolet is here on the left. And very low energy, like infrared or red, is on the right. This is low energy. Ultraviolet is what gives you cancer. Gamma and X-ray give you cancer. So on the left are the dangerous ones, the high energy, the small wavelengths. So small wavelength is able to damage your DNA because it's as big as your atom. It's the size of an atom, so it can cause the atom to go into self-resonance, and then it breaks down. It flies off. You basically you break the DNA, and you could create one out of many will create a cancerous cell. You'll actually kill the telomeres, and you'll get cancer. So that's the high energy on the left. So how much of a high energy? You always have very little high energy and very little of low energy. Most of it is at the center. And at high temperature, this is okay. Of high energy, you get, as you go to higher and higher, lower and lower energy, you get less and less of it. You get more and more of it. As you go into lower energy to the right, you're getting more and more incidence, more and more of that wave, more and more intensity. Higher intensity of the wave of this color, of this frequency. And the maximum frequency, the maximum, not frequency, but the maximum intensity. This is the radiance is the intensity. Okay, I'm going to stop talking because I'm falling asleep.
A second per unit area per unit wavelength, which is simply the intensity per unit wavelength.
Okay, that makes sense. Well, the intensity is just the amplitude, I would say.
And since intensity is defined as...
It's not exactly amplitude, it's how many, right, for each delta wavelengths, what is, how many, or whatever. I'm not talking anymore, I'm falling asleep, putting myself to sleep.
Power per unit area, it follows that the units of spectral radiance are watts per cubic meter.
Okay, this is watts per cubic meter. Okay. Why is it watts per cubic meter? Because watts per meter squared, I don't know why this is watts per meter cubed of the box. How many watts are in the box? This is the box, maybe?
To find the intensity from one of these graphs, you simply have to find the area beneath the curve. In other words, the intensity is the integral of the spectral radiance with respect to wavelength.
Oh my god. So the intensity, he said intensity or intensity? I think intensity for a temperature is the integral from 0 to infinity of the radiance at lambda d lambda. So you basically find the area under the curve, and that gives you the total intensity. Okay.
Is the integral of the spectral radiance with respect to wavelength.
Oh my god. I'm not gonna make it. My brain is shutting down all the time. I'm gonna have to take a nap.
Experiments like these revealed patterns in the data. In particular, two striking empirical laws emerged. The first of these was the Stefan-Boltzmann law, which related the intensity of...
So Stefan-Boltzmann law is basically this distribution, and this describes, for example, wealth distribution in a free economy. Why is that? It also describes the motion of molecules or particles in an ideal gas, which means, right, there's very few particles in an ideal gas that move, let's say, at zero speed. This is the zero speed, the slowest ones. But fast ones, you can have infinite. There's no limit on infinitely fast moving particles. Okay? And wealth, well, you're limited at zero. You cannot be negative, because then you just declare bankruptcy. So you can only be poor. There's a limit to how poor you can be, but you can be infinitely wealthy. So this is the Boltzmann-Wallace or Boltzmann-Maxwell distribution.
The first of these was the Stefan-Boltzmann law, which related the intensity of the emitted radiation.
What is intensity? I don't know. Never heard of intensity. Maybe he means intensity.
With the temperature. You can clearly see from the graph that as the temperature increases, the area under the corresponding curve increases, and therefore the intensity increases.
He keeps saying intensity. What is intensity? But anyway, as temperature goes up, the total area under the curve goes up. That's very straightforward.
The Stefan-Boltzmann law quantifies this relationship and says that the intensity is proportional to the fourth power of the temperature.
So this can be derived. This is the Stefan-Boltzmann law. You can derive it somehow. Nobody knows how. I'm kidding. That the temperature to the fourth times sigma, I don't know what sigma is, that gives you the total intensity. I guess is the total intensity. I guess it's the integral of the radiance. I don't know.
The second empirical law is the Wien displacement law, which relates the wavelength corresponding to peak spectral radiance law temperature, and says that the intensity is proportional to the fourth power of the temperature. The second empirical law is the Wien displacement law.
So this is the fourth power of the temperature. So the temperature, maybe you can compare to the economy. So this is maybe the total money in the economy or something, the total wealth in the economy. Yeah, it's the total wealth. No. Yeah, maybe. This is like how many people are in the population that are this wealthy. How many people that are this wealthy? Well, this is the radiance is the number of people of this wealth. Number of people is this one, is the y of this wealth. And this is the mean. The average is like no, I don't know where the average is. So there's the average, there's the median, you can calculate them, there's a definition. These are just mathematical definitions. But as you get wealthier and wealthier, you can, and this is why you have inequality. This explains why you have extreme inequality, but this is why it's not important to have extreme inequality. Why? I mean, there's, like, imagine, like, this economy, there's just more wealth in this economy compared to this economy. So in this economy, a lot of people, there's so many people who are this rich, but there's fewer and fewer. This is called a long right tail and a short left tail. So a long right tail, or an infinite right tail, means you can have people of vast wealth, but very few of them. And you'll go and go further and further to the right, and there's another few super wealthy. You keep going, there's two more and one more, and that's it. So so you have, right? So when you look at the inequality, oh, there's so much inequality. But why do you care? Why do you care that there is inequality? Why do you care? I mean, why do you care that there is a person who is super duper well? Why do you care? All you care is what is the average quality of life of a citizen. The question is, I mean, there are some very poor people. Why do you care? Okay, some people lost everything. They gambled everything. Whatever happened to them, they were born with some mental issues. Okay. Anyway, let's get back to wine displacement law. What is wine displacement law? I don't know. But why is it t to the fourth? I don't know.
Which relates the way it says that the intensity is proportional to the fourth power of the temperature.
The intensity is proportional to the fourth power, which is the total area under the curve, which is like a total wealth, or the total motion of particles in a volume, if it's an ideal gas.
In empirical law.
Alright, so this graph explains three phenomena. One is black body radiation. Another one is ideal gas. Motion of particles, distribution of motion of particles. In quantum physics, this experiment relays the distribution of wavelengths, distribution of intensity per wavelengths, or radiation per wavelengths. Let me see. Oh, they're trying to call me? Are they trying? I need to tell them that I'm busy, not now. Where can I call them? Where can I let them go? Let them know. I don't know what's going on. We said we're gonna have a phone call together later. Let's see, typing. Okay, we'll get the message later. Anyway, so in an ideal gas is the distribution of the average of the motion of particles. Let's see. Okay. So it was just a mistake. Okay, so and wealth distribution is like the distribution of wealth in a population. So there is very few people. Ultimately, there is 0 people with 0 wealth. Like there's no such thing, or something of that nature. Then there is very few with very little wealth. And there's also very few with very much wealth. But like with particles, you can have very few particles that are not moving, very few that are moving faster and faster, but there's no limit to the speed. Right? You could have a particle in an ideal gas moving at almost the speed of light. Yeah, but it's an outlier. You're allowed to have that. There's going to be one particle traveling almost at the speed of light. Just, in a random ideal gas distribution. Okay. And as far as radiance is concerned, so as you heat it up, you have more energy, more intensity or intensity. Intensity is the total area under the curve. It's how much light is this thing emitting. How much total light. As it heats up, I think the center of mass starts moving to the left. So it's whiter or bluer. Whereas if it's cold, it's redder. So the red shifts as it cools down. And it blue shifts as it heats up. Until it gets like if you heat it up maybe more and more and more and more and more and more and more, it's gonna ultimately average at the ultraviolet. But anyway, you always have part of the distribution is ultraviolet. The hotter it is, the more. Yeah, you have a few of these at ultraviolet. Here you have, let's say, none at ultraviolet, and very like even less than none at ultraviolet. So, but this is ultraviolet. So for any given temperature, you have some of the wavelengths are going to be very very short, very dangerous. Some are very long, very not dangerous, and some center of mass. Okay.
Is the Wien displacement law, which relates the wavelength corresponding to peak spectral radiance with the temperature. As the temperature increases, the wavelength corresponding to maximum emission reduces.
Okay, so this is not. I was thinking about the center of mass. He doesn't talk about the center of mass. He's talking about the maximum. So let's say this is the maximum here, and as you heat it up, the maximum moves to here, and as you heat it up, the maximum moves further to the left. So the maximum blue shifts as temperature goes up. This is lambda of the maximum radiance, not the maximum lambda. There is no maximum lambda.
This fits with
which makes it it becomes more and more dangerous.
What we have already seen when heating a lump of metal. As the temperature of the glowing metal is increased, its colour changes from red to orange to yellow, which corresponds to shorter and shorter wavelengths of light.
Yes, I completely agree. Let's check the audio. The audio is good. Let's listen to the audio. Oh, it's on my iPhone. 1 second. Let's hear it. Yeah, it's good audio. Very good audio. I love the audio. It's very good. It's delicious audio. Very delicious. No, don't call me again. Oh my god. They keep calling me, so I have to take this call. Oh my god. Yeah, I'm gonna have to take the call. 1 second. I don't know what's going on. No, I can't. 1 second. 1 second. 1 second. But where? I can't see the phone calls. Jesus. Let me see the phone calls. Are they talking? Can I know if they're talking? Yeah, they've joined the conversation. Let me listen to what they're saying. Give me a minute. Okay, so I'm gonna shut down. I'm gonna leave this, and I'm gonna shut this down. All right. All right. We're back. We're back, baby. We're back, baby. Okay. So we may continue. Let's make sure the audio is good. Okay, the audio is good. Let's continue. So we have some comments. Nicholas, this is your field of Planck. We're studying actually Planck's experiment. If you increase the frequency, you reach a point where you simply start contributing energy to the Planck field. I don't know what the Planck field is, Nicholas. You're at the scale. I don't know. I don't know anything. But I think you're watching, so you can join me if you want. But you know. Anyway, let's continue watching this video.
And this is encoded in the Wien displacement law.
Let's hear it again.
From red. This fits with what we've already seen when heating a lump of metal.
Right, when you heat a lump of metal, it glows from the red to the white.
As the temperature of the glowing metal is increased, its colour changes from red to orange to yellow, which corresponds to shorter and shorter wavelengths of light. And this is encoded in the Wien displacement law.
So the Wien displacement law says something very simple. It just says that it glows in whiter and whiter. Yellow from red to white, from red to yellow.
And this is encoded in the Wien displacement law.
So as t goes up, lambda goes down, meaning lambda times t is a constant. So it's basically, what do you call this? You call this a hyperbola. It's a hyperbola. 1 second.
Although the Stefan-Boltzmann law and Wien displacement law provided valuable insights into...
So the Stefan-Boltzmann law is just this distribution. Stefan-Boltzmann is the distribution of the speed of it's a mathematical derivation of the speed of particles in a gas. That's all it is. 1 second. Okay. I used to hear Destiny make these noises. Now I know why. It's because it's to wake up the brain. It's like when you make these noises, you sort of wake up the brain just a little bit. Otherwise, the brain falls asleep. At least my brain. This is so confusing. This stuff is impossible. Anyway, so the Stefan-Boltzmann, as far as I'm concerned, is the distribution of the motion of the speed of gas particles in an ideal gas. It's just the distribution of the speed. Whereas the other one, what was the name of the law? The displacement law, the Wien's displacement law. That's it creates. Is it? No, it's not a hyperbola. It's like a linear. It's like a logarithm. It's a logarithm. It looks like a natural. It's a natural logarithm looking distribution of the maximum. Just if you want to show the distribution of temperature times maximum lambda is a constant.
And this is encoded in the Wien displacement law. Although the Stefan-Boltzmann law and Wien displacement law provided valuable insights into black body radiation, theoretical physicists wanted more. Firstly, they wanted to know what the spectral radiance function was. And secondly, they
wanted to know what is the radiance of lambda function. They wanted to have a mathematical or a physical derivation, a theoretical derivation. This is just data. This is empirical data. But what is the mathematical theory that creates this distribution? So in an ideal gas, it makes sense. But with a glowing piece of metal, what are you saying? So I would say it's just the distribution of the vibration of molecules, of atoms in a metal box. So some atoms are going to be shaking at this rate. There's more of them vibrating at this rate. This is the maximum. At this maximum vibration, there is this many. And at very low vibration, this is very low frequency, there's very few. And when you go to lower and lower and lower frequency, right, because you can have, well, you're limited by lambda. Lambda is limited to be 0. You cannot have a wavelength smaller than 0. It's actually limited by the motion of the electron, right? You're vibrating an electron. It's just thermodynamics. And there is just a distribution. Just like with moving atoms, they're not interacting. They say it's not interacting. I don't know how that could be. It's just it's just some sort of distribution. Maybe it's picking up energy from the box. So this is picking up energy. I don't know from where. Oh my god. Anyway, but I could come up with with a simple model of vibrating electrons in atoms. So vibrating atoms, right? Why do things glow? It's right, if you're vibrating the electron, that's creating a vibration, which is an electromagnetic wave. That's light. So you're just shaking the atom. So if you're shaking the atom, so you're going to have all sorts of a distribution. So you cannot have, right, as you're looking for things moving faster and faster and faster and faster, because of the frequency, because the speed of light is, the speed of light is a constant. Because the speed of light is a constant, you cannot, the electromagnetic radiation cannot move faster than the speed of light. It always moves at the speed of light. So as you're looking at shorter and shorter lambda, meaning the electron is moving faster and faster, it's limited in how fast it can move basically by the speed of light, because so there is a limit. Whereas everywhere else there is no limit. Like for longer and longer wavelengths, there's no limit. It can move as slow as it wants, and then it can have as longer as lambda as it wants. And there is a certain distribution. For a certain temperature, there's a certain distribution. And that's it. Problem solved. Why was there an issue to begin with? Where's the issue?
We wanted to be able to derive an expression for the spectral radiance using the known laws of physics. And so this is what Rayleigh and Jeans did. They turned their attention to the theory. So this for the was.
Okay.
And secondly, they wanted to be able to derive an expression for the spectral radiance using the known laws of physics. And so,
can radiance of lambda be derived from the known laws of physics? That's a good question. Can the radiance as a function of lambda be derived from I would say so. I can derive it. I can derive a model.
This is what Rayleigh and
what do you mean, what is the radiance?
They wanted to know what the spectral radiance function was. And secondly,
they wanted to have a mathematical description. That's the first. And second, they wanted to be able to derive the mathematical description from a theoretical foundation.
They wanted to be able to derive an expression for the spectral radiance using the known laws of physics. And so this is what Rayleigh and Jeans did. They turned their attention to the theoretical study of radiation inside the Jeans cube and applied the best theories of the day to tackle this problem. So what were the known laws of physics? Given that Rayleigh and Jeans wanted to study the radiation properties of a black body, it made sense that they used the highly successful laws of electromagnetism, and in particular the recently discovered properties of electromagnetic radiation, as elucidated by James.
Wait, this is wrong. Isn't this wrong? Isn't it just the opposite? That, right, that a change in electric causes magnetic, but there's no change in electric. This is zero change. This is literally zero. This is the first derivative of the electric is zero. There's no change in electric here. If you stand here and if you hold x constant and you move time, so the wave will pass through. But right now, at this instant, the intensity of the electric field, the V, let's say it's voltage dot, the change in voltage over time, right here it's zero. There's no change over time. As the wave passes through, this is a stationary point. At this point, the first derivative is zero, and the first derivative is the magnetic field. So at this point, the magnetic field should be zero, but it's not. It looks like the magnetic field is equal to the. It looks like they come and go together. That doesn't make any sense. That's not what. That's not these are not the laws of Maxwell.
Clerk Maxwell. According to Maxwell, light consists of a self-propagating.
Magnetic field is E. Electric field is also E. Why are they both E? Usually magnetic is B, and the magnetic is usually right to left, and the electric is up and down. The electric should be E, and the magnetic should be B, and the magnetic should be the blue. That's usually the way it is. I don't know.
Electromagnetic wave that travels at the speed of light.
Because this way, whatever, fine. I don't care.
Through a vacuum. Radiant genes
what?
also
What do you mean
at
through
the
a
speed
vacuum?
consists of a self-Clerk Maxwell. According to Maxwell, light consists of a self-propagating electromagnetic wave that travels at the speed of light through a vacuum.
No, not through a vacuum, through the ether. No, this is wrong. Did anybody correct him on the graph? The graph shows up at 8:38. Why am I understanding this? Where were you? Okay. As someone, I am whatever. This is the third. YouTube would have loved. I've studied. No comments, just compliments. I hate compliments. They should move compliments to the end. It's useless to write compliments. And everyone give, yeah, it's great. I agree, it's great, yeah, but it's just, we need to have a discussion, not just compliments. I want to say thank you. Oh my God, I want to kill myself. No one says here, I want to kill myself. Oh my God. Why does no one here say I want to kill myself? Okay, here is somebody saying something. Oh wow. Oh my God. Oh my God. Jesus help me. Oh my God. Oh my God. Please Jesus. Please Jesus help me. Help me Jesus. What's the evidence that Jesus doesn't want to help me? This is the evidence. As evident by this, Jesus does not want to help me. Oh my God, very well done, fantastic, oh my God, I've also the name, it's also the name, oh my God, please kill me, somebody please kill me, please kill me, oh my God, this is too painful. Too painful. Okay, let's just load more and more messages. More and more and more and more. What do I sound like? Okay, so let's look for Well, what did I want to? I don't remember what I wanted to ask. Two things. Oh, in a vacuum. So vacuum. Oh, the solution of that catastrophe was truly marvelous. Yeah, nobody's saying that. Okay, there it is. 8:30. Light travels at the speed of light in a vacuum, which is true, but not very descriptive. It okay. So awesome video. Loved it. I do have one tiny complaint at 8:30. You say light travels at the speed of light in a vacuum, which is true, but not very descriptive. It would be like saying the car traveled at the speed of a car on the road. You should have said light travels blah, 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 in a vacuum, which actually gives your audience information. Okay. Yeah, that's not what I wanted to say. I don't care. It's not in a vacuum. No one believed in a vacuum. In those days, they believed in the ether. The luminiferous ether. Where all these are the names of videos. Okay. So the solution, I don't care. Like, okay. So no one is talking about it. And what about the electromagnetic waves? Wave. Oh, there's too many. Waves. I used to think that the standing waves, end waves because it ended also. Okay. Okay, that's it, no more. Waves that I have ever seen. This is standing waves, I don't care. Neither waves nor particles can do this. How can we account for light speeding back up to its normal speed? I don't know. Okay. Anyway, no one is discussing these 2 points, so I don't know. Should I mention this? This is 8:33. So 8:33. You show that the electric and magnetic waves are in unison or synchronized? Are synchronized, are in sync. In sync. However, according to Maxwell, a change in one induces the other. But at the max value, the change is min or 0. So should not they be perfectly out of sync? That's question 1. Question 2 again at 8:33. 8:33. So, I mean, both magnetic and electric fields are E. Well, both electric and magnetic are E. That's weird. Okay, third question. Still at 8:33. Yeah, what do you want to know? In a vacuum. In a vacuum. But did they not believe in the ether? Okay, that should fix everything.
Rayleigh and Jeans also turned to the statistical laws of thermodynamics as put forward by Ludwig Boltzmann.
Okay, Boltzmann was like the ultimate genius when it came to statistical mechanics, which is just the motion of particles in an ideal gas. All right.
According to Boltzmann, the temperature of an object is simply a statistical average of the energy of the particles comprising the object. Armed with Maxwell's electromagnetic waves and Boltzmann's statistical thermodynamics, Rayleigh and Jeans were confident that they could successfully derive the spectral radiance function for a black body. They just needed a clear strategy. Firstly, they realized that it would be more useful and simpler if they specified the spectrum of radiation inside the Jeans cube in terms of the energy density rather than the spectral radiance. And
energy density, rho of the frequency. I don't know what that means.
so this is what we are going to do. The energy density is simply the energy contained in a unit volume of the cube at temperature T in the frequency interval between F and F plus dF. Once the energy density has been established, the spectral radiance can be calculated very simply, since the spectral radiance and energy density are proportional to each other.
I don't even know the difference.
In fact, the spectral radiance is equal to c over 4 pi times the energy density.
Why is that? Why is the speed of light being mentioned here?
And we'll return to this result later.
What is rho? Rho is the density, it's the energy density, and R is the radiance. I don't know how they measure. He's not showing the measuring. It's not showing the apparatus. So this is 946. You are not showing the experiment apparatus. Is that's not the way you spell apparatus? Maybe double P. Yeah, you're not showing the experiment apparatus nor the experiments protocol. It is very difficult to understand this video. However, this is the best YouTube video on the subject thus far, obviously. Okay.
Okay, but how do you find the energy density? The approach of Rayleigh and Jeans...
I mean, he's not explaining the equation. I mean, can you explain this equation? Why is radiance and density related this way? Why do you multiply by c over 4 pi? I mean, where does that come from? So radiance and density are related by c over 4 pi. Why? Well, that doesn't make any sense. I wish I could click like the time, like in the iPhone, it lets you choose the time. So this is 9:46. Oh my god, this is going to be impossible. So R is R of F is equal to this times rho of... Wait, I have Greek. Let me switch to Greek. This is rho. This is phi. I need F. So I should have pi as well. Okay. Oh my god, this is impossible. Can you please derive this equation? Oh my god. Okay. Let's see. Okay, we're in the room. Let's see. Audio level is 100%. There's 2 people watching.
I times the energy density, and we'll return to this result later. Okay, but how do you find the energy density? The approach of Rayleigh and Jeans was threefold. Firstly, you need to count the number of electromagnetic waves that fit inside the cube. Secondly, you need to calculate the average energy of these.
Count the number of waves that can fit inside the cube. Why would you want to do that? This is so confusing. Why would you care? I mean, could you explain why? I mean, I have more questions than I understand things. Like every sentence you say here, I don't understand. Why? Count the number of waves that can fit inside the cube. What are you talking about? This doesn't make any sense. Where did this come from? Calculate the average energy of these waves. What does that even mean?
Waves when in thermal equilibrium.
What do you mean thermal equilibrium? Okay, like after you heat it up and it comes into thermal equilibrium with the room. Okay.
And finally, you combine these two results to find the energy density for a particular range of frequencies. So let's do this.
Okay, this makes no sense. This is putting me to sleep. This is so depressing.
To begin with,
this is the foundation of quantum mechanics. This is the foundation. Everything sits on top of this experiment, and I've watched so many videos. No one explains it. This is the most explanation we get on YouTube. We basically need to read a modern physics book.
We need to understand how to mathematically describe waves. Since we are going to describe the radiation inside the cube in terms of electromagnetic radiation, which, as already discussed, consists of waves. We can describe the energy density for a particular range of frequencies.
I'm going to have to take a break because I'm just falling asleep. This is way too difficult. This video is just, I thought it's going to give me so much insight. So far, almost none.
So let's do this. To begin with, we need to understand how to mathematically describe waves.
How to mathematically describe waves? Why do you want to mathematically describe waves? What are you talking about? What's your? I don't understand your strategy.
Since we are going to describe the radiation inside the cube in terms of electromagnetic radiation, which, as already discussed, consists of waves. We can describe a wave travelling to the right using the following sine function. Here, y represents the displacement of the wave for a given x coordinate and time coordinate. Since the largest possible value of the sine function is 1, we see that capital A represents the amplitude, and this is the maximum possible displacement. So, if for example this was a wave on a rope, A would represent the maximum height that the rope moves away from equilibrium position. The minus sign tells us that the wave is moving to the right, and if we let time flow, we can see this. The constant k is referred to as the wave number, and it's defined as 2 pi.
So as t moves up, the wave moves to the right?
Pi over lambda. It represents wave number, and it's defined as, and if we let time flow, we can see this.
But why is it as t goes up, why does the wave move to the right? Why does that happen? So any graph, I think any graph, if you remove, right, t is, right, there is x and there is t. T, we don't see t. We don't see t, so as you increase t, right, t in the beginning is 0, so you're not deducing anything. But then you're saying sine of less than 0. So sine of less than 0, So the clock is ticking clockwise, right? So you can imagine, right, sine, the sine of the angle. It's the sine of the angle. So as t increases, the clock is ticking to the right. So the sine goes negative and then positive and then negative and then positive. So if you take one position, so it goes down, and well, in the beginning it goes down and up. I guess, yeah, I guess it makes sense. I don't know, whatever. I don't remember my wave mechanics from 1,000 years ago. So for the same value, you reduce the angle by just a little bit, and this entire wave should move to the right by just a little bit. Right? If you take this point, in order for this to move to the right, right, so yeah, it goes down by just a little bit, right? It goes down by just a little bit initially. But what about this point? So this is 0. From 0 it goes down. It moves to the right and goes down. Yeah, it makes sense. It's true.
The constant k is referred to as the wave number, and it's defined as 2 pi over lambda. It represents the spatial frequency of the wave. On the other hand, omega...
Okay, so this number k, so k is a whole number? Did he say k is a whole number? Where can I... How far do I have to go back?
Consists of waves. We can describe a wave travelling to the right using the following sine function. Here, y represents the displacement of the wave for a given x-coordinate and time coordinate. Since the largest possible value of the sine function is 1, we see that capital A represents...
Capital A is very straightforward, no issue there.
...the amplitude, and this is the maximum possible displacement. So, if for example this was a wave on a rope, A would represent the maximum height that the rope moves away from equilibrium position. The minus sign tells us that the wave is moving to the right, and if we let time flow, we can see this. The constant k is referred to as the wave number, and it's defined as 2 pi over lambda.
Okay, so it shouldn't be, it's not a whole number, but it's 2 pi over lambda. Why is, so let's say lambda is 1. No, let's say lambda is 2 pi. Then k is 1. Then at x, sine of, well, I want it to be 0. Let's say x is 0. So, no, but as we move on x, as we move to the right on x, as x grows, the clock is ticking clockwise. From 0, down, up, that's fine. But if we increase k, then we need to move less with x to get faster and faster. So the clock moves faster and faster, and the wavelength is, I think, shorter. So the bigger number, the bigger k, the smaller the wavelength. Okay, that makes sense. Why is it 2 pi over lambda? I don't know.
It represents the spatial frequency of the wave. On the other hand, omega is simply proportional to the frequency of the wave.
Wait a minute. Oh, so if c is given, then there is a relationship between lambda and omega. But omega is just 2 pi frequency. I think this should be derivable. We should be able to derive this equation given certain conditions. If you tell me given that a wave has this amplitude, and at 0 it's this value, and at 1 it's this value, then derive the equation. That should be doable. So if we take measurements, we should be able to produce the function.
And that's the temporal frequency, i.e. the number of complete waves passing a point each second. Now we can likewise write down an expression that describes a wave moving to the left, and you see that the minus sign has been replaced with a plus, and this causes the wave to move to the left. So what would happen if we had a right moving wave encountering a left moving wave in the same region of space? Well, in that case we would refer to the principle of superposition, which states that the net displacement at a location in space is simply the sum of the individual displacements at that point. So if we wanted to find the net displacement due to our right moving wave and left moving wave passing through the same point in space, we simply add the individual displacements. Now, we can simplify this expression by using some trigonometric identities, in particular sine of a plus b and sine of a minus b. If we add these two trig identities...
Okay, so this is sine of a minus b and sine of a plus b. So sine of a plus b is sine a cosine b plus sine a sine b. So if we do the replacement...
these together, then we find this...
I mean, sine a plus b, we need to be able to derive this. I don't know how to derive this. Okay, so sine a minus b plus sine a plus b is 2 sine a cosine b. So this is what he got from this. Okay, whatever.
Purple expression, sine of a minus b plus sine of a plus b equals 2 sine a cos b. Now if we match up terms, we see that a can be identified with kx and b can be identified with omega t, and therefore the net displacement can be written as 2a sine kx cos omega t. So what does this look like? Well, we can visualize it with the following animation. You see that the left and right moving waves add together to form the green wave.
He shouldn't show them on top of each other. He should show them in 3 rows or something.
Wave. And if we remove the left and right moving waves and just focus on the net displacement, we get the following stationary wave pattern.
That's amazing.
It's called a stationary wave pattern for obvious reasons,
It's not
because
moving
the
to
pattern
right
isn't
or the
moving
left.
left or right, it's just moving up and down.
Amazing.
So, how does this relate to the electromagnetic radiation inside the Jeans cube? Well, let us assume that the Jeans cube is aligned along an x, y and z axis, and that the length of each side of the cube is L. Then the electromagnetic radiation reflecting back...
Okay, we're going to take a break soon before I kill myself, so that I have time to kill myself. Otherwise, I'm not going to have enough time to kill myself, and that would not be very good. I would not be very productive if I don't kill myself. At least a little bit, you know, just a little bit. A little killing myself needs to be done. Let's see how we're doing with the audio and the video. Needs to be done. Let's see. Very good audio quality. I love the audio quality. So good the audio quality. Oh my God. Does anybody want to talk to me? I need to wake up. Please, somebody talk to me. Somebody, please talk to me. Okay. Let's see. Andrew. Hi. Where are you? Ugh. Gordon. Okay. Okay, who else? Amber. Okay. Judas wants to take a break. Cenas. Okay. Nick. Oh, Karen. Lily. There's no one else. No one else in the universe. Okay. Let's continue just a little bit more.
And forth can be analysed into three components. Consider the X component. All the radiation along this component which is incident upon the wall is reflected by it, and the incident and reflected waves combine to form a stationary wave along the X direction.
Okay, I don't know where it's
The
going
incident
with this
along
one.
this component, then the XY the gene's cube. Well, let us assume that the gene's cube is aligned along an X, Y and Z axis, and that the length of each side of the cube is L. Then the electromagnetic radiation reflecting back and forth can be analysed into three components. Consider the X component. All the radiation along this component which is incident upon the wall is reflected by it, and the incident and reflected waves combine to form a stationary wave along the X direction. Since the electromagnetic
How does he know this? How does he know what's going on inside a black box? I honestly don't know.
radiation is a transverse vibration, with the oscillating electric field perpendicular to the propagation direction, and since the propagation direction is perpendicular to the wall, it follows that the electric field is parallel to the wall. However,
Yeah, I mean, I can agree with that. Somewhat. Right, the only resonance you're gonna get, okay, I'm beginning to agree with this. So you have a bunch of atoms inside here all vibrating every which way, but only the electrons moving up and down that are creating the up and down waves, only they can become resonant. Only they will survive in the long term. The rest of them will destroy each other and it's just gonna be noise. But the actual laser, the resonance, the self-resonating, the self-enforcement, basically it's a laser. This is basically a laser. Now that I'm thinking about it, this is basically how a laser works. You're resonating these back and forth with a tiny hole over here, and it shoots out a laser. That's exactly what a laser is. They just put two mirrors here.
a metallic wall cannot support an electric field parallel to the surface, since electric charges can always flow in such a way as to neutralize the electric field. Therefore, the electric field must be zero at the walls of the container. That is, the stationary wave associated with the X component of the radiation must have a node, aka zero amplitude, at x equals 0 and x equals L. These conditions put a limit on the possible wave.
That actually makes sense. So you can't say that, right? There's no resonance inside the wall. You can't tell me that this wall is behaving like an antenna of a certain frequency. That doesn't make any sense. What you have here is many tiny electrons vibrating up and down. The right and left ones are not gonna do anything in terms of this resonance. So only the up and down ones are gonna create waves going back and forth of different frequencies, of different wavelengths. So the ones that will survive are the ones like this one, and this one. One second, somebody's responding. Who is that? Hamburger. Uh, I'm dying of boredom. Oh my god, I think she's here. One second. Hey, what's up? I'm so tired.
Oh, not much. I'm like photoshopping pictures of people. Oh, I'm echoing.
Oh, you're echoing?
Mhm.
Let me fix the echoing. One second. Give me a second. Yeah, give me a second. Let me fix the echoing phenomenon. The phenomenon of the echoing. The echoing phenomenon. Okay, so I'm gonna tell it to echo cancellation. Okay, I do echo cancellation, then I'm gonna move out and in. One second. Out, in. Okay, is it better now?
Let me see.
1, 2, 3, 4, 5.
Yeah, okay, I
Oh,
can't
it's
hear myself anymore.
okay. That's good. So here, if it comes back, let me know right away, and I'll kill myself.
Okay.
Yeah. Anyway, well, how is your life these days?
Pretty good. My fiance got back from his business trip, so we were having a good day.
That's incredible. That's terrific.
My ex was being really fucking toxic. Like, he was calling me and telling me to die and, like, calling me a whore and shit. And it was
Tell him
pretty
to call
intense.
me. Tell him to call me. Maybe he can wake me up when I do these deep dives into physics, and I need somebody to call me names to wake me up. Ask him if he wants to come and call me names. Do you think he would do that
I'll
for me?
try. That would be funny, but I think he's finally, like, fucked off. Like, he was just offering all this, like... Oh, excuse me. No, but he was offering to, like, do a lot of the stuff that he promised me he would do during our relationship, but he didn't go through it. And I was like, why are you offering me this now, but you didn't do it when I actually wanted to be with you? Like, that's just kind of, like, not accepting that I moved on, and it doesn't seem like coming from a healthy place, like you actually want to do it. It just seems like you just don't want me to be with this guy because it makes you feel bad about yourself. And, like, he like
Mm-hmm.
said it wasn't, and then like all this other shit, and then I was like, whatever, I gotta go to bed, and then I went to bed, and he started
Mm-hmm.
texting me a bunch of shit, and I was like, why do you keep getting into an argument with yourself whenever I leave the conversation? Like, that's why I didn't like dating you,
Mm-hmm.
because every time I would walk away from a conversation or something, he would start like DMing me all this crap where he's
Wow.
just getting into a fight and saying like, you must not be the person I thought you were, like if you don't like care about this or whatever. And it was always like religious stuff. And
Mm-hmm.
like my fiance is like religious too, but he doesn't behave like this, and that's
Mm-hmm.
why I was kind of thinking maybe my ex has like schizophrenia
Okay.
and is just really like obsessed with stuff, and also he
Mm-hmm.
doesn't seem like he holds a job good. Like he kind of reminds me of like another ex I had with schizophrenia, where it's like
Oh.
they're really good at tech stuff, but like they don't apply themselves because
Oh.
they're so all over the place that they
Oh.
just like
Mm-hmm.
they kind of just do drugs and have quote unquote experiences. It's like they think that they're actually having like experiences when they're on like Molly or something, and it's like just psychosis. You know,
Mm-hmm.
it's actually kind of sad, and I can't put up with it, which is why we ended up breaking up. And also because he kept ODing, and
Mm-hmm.
like I'd be there for it, and then he would just like start like praying and shit, and I would be like, dude, like I can't have you like having a heart attack and stuff, and then he just like
Mm-hmm.
you know, he'd be like, "Oh, I'm fine," and then he'd kind of be like, "I need to start doing this less," and then he just wouldn't, and he would say he was okay, and that like the government lied about how bad drugs are, and that like I don't know what I'm talking about, and I'm just like, "Well, dude, I watched you almost die." Like that's not a government conspiracy. That was honestly like a distressing experience, and he
Mm-hmm.
would just be like, "No, I was fine."
Mm-hmm.
Fucking constantly, it was horrible.
Wait, I'm gonna end the previous stream and I'll create a new stream. You can. I'm listening to you. It's interesting. I'm just doing stuff
Alright,
in the
yeah.
background.
But yeah, he would also like yell